Okay, so hi everyone. So today I'm going to be talking about a paper of mine from, well, it came up online last summer, and we've since updated it a little bit and only just submitted it to a journal very recently. And so the title is Statistical Inference for Generative Models with Maximum Mean Discrepancy. I'll often be calling this MMD. And maybe some of you will have encountered this already, mostly because there's a lot of research on MMD here at UCL. But if you haven't, don't worry, I'll be introducing everything from scratch. So if you could mute yourself if you don't have a question, that'd be great, because I'm already hearing some, some keyboards. And yeah, but otherwise, if you do have a question, feel free to just jump in anytime. I don't know if there's a chat on Zoom, but please don't write in the chat. Just interrupt me and ask the question. I think it's a lot easier this way. Okay, so the main topic of the talk is going to be about, well, as the title says it, inference for generative models. And the talk will be mostly from a statistical viewpoint. So obviously I'm aware that this is the AI Center seminar series, but what I'll be doing is mostly talking about generative models from the point of view of statistics. What sort of tools from statistics could you use to do inference for these kind of models? And then talk a little bit about the connections with machine learning and what's been done, for example, in the GANs literature. So you can think of my talk as a statistician's viewpoint on MMD GANs, and I'll make that a little bit clearer as the talk goes on. So, okay, so before I start, yeah, the paper's on arXiv, you can go and check it out if you're interested. It's joint work with a couple of colleagues from Imperial in Cambridge. So let's get going. So the main problem that I'm going to be discussing in this talk, and which is really just a big problem for statistics, but also machine learning, is that models are getting more and more complex. And what this means is that often some of the tools that we were used to applying are not usable anymore because we don't have access to certain quantities that we used to use for pretty much everything. So in this case, it's going to be the likelihood. So most methods in statistics and machine learning are based on the likelihood. So obviously, maximum likelihood estimation is based on the likelihood. Bayesian inference also requires the likelihood. And so there are, when models are very complex, you in fact do not have access to the likelihood. And so you're a little bit stuck because you don't really know how you should be doing inference. And so in recent years, now when I say recent years, it's been quite a little while now, people have started to come up with alternative methods to do inference, i.e. if I give you some data, recover some parameters of the model, and to be able to do so without the likelihood. And so I'll be talking a bit about that for the next few slides. So in this talk, I'm mostly going to be talking about generative models. So informally, what my definition of generative model will be is just a generative model will be a class of probability distributions such that for any fixed element, I can easily sample data in a IID fashion. And that's the only thing that I know about the model. So I don't know the likelihood, for example. And as I mentioned, that's something that's coming up more and more in practice. So, sorry? Oh, okay, I'm not sure. So let me just give one example. For example, in astronomy, physicists are quite good at developing models of galaxies. And how do they do that? Well, they use the laws of physics and they simulate to get realizations of galaxies. Now, maybe in this case, what a model would look like is the parameter would be something like the initial, I don't know, state of the universe, and then you simulate, and then you get realizations of possible galaxies, for example. So in that case, well, even though it might be fairly easy, and when I say easy, take this with a pinch of salt, but it might be doable to simulate galaxies. It's certainly not going to be easy to write down the likelihood for this model, and therefore doing inference for certain parameters is going to be difficult. And the story kind of repeats itself for other fields, so in ecology, in genetics, etc. And of course, in machine learning, the same is true. So I'm sure most of you will have heard of generative adversarial networks. These are generative models that people normally use to generate realistic to some point, depending on how good your GAN is, but model of images. So what happens is that you give the method some examples of images, and then the generative adversarial network learns how to generate new images. Okay, so that's obviously a class of models which have a range of applications that I've mentioned. And so we'd like to know, okay, how do we actually do inference for these kind of models? So the first one is, well, the first question that you should ask is, well, how do we do inference if we don't have access to the likelihood? I've already mentioned that's kind of usually the starting point. Well, one option to do this is minimizing some notion of distance between the data and the model. So if the model is, I called it earlier a family of probability distributions, then you could just look at what's the distance between that probability distribution and the data, and perhaps choose the element of the family that makes this the smallest possible. Okay, well, that's potentially a reasonable thing to do. But of course, the kind of main question is, well, which distance should we use, and how should we pick a good notion of distance between data and model? And that might seem like a technical question, but actually it's going to have a really big impact in terms of what you will learn. And so it's actually a very important point. And what I'll argue in this talk is that one possible choice for this distance is this maximum mean discrepancy. And I'll highlight some of the advantages and disadvantages of this particular distance in terms of the properties of the method. And then finally, one question which will matter a lot more in practice is, how do you actually implement these minimum distance estimators? And so I'll touch upon that a little bit and show how you can use kind of efficient optimization methods to do so. Okay. So that's kind of the kind of timeline of the talk. I'll first talk a little bit about problems with lack of access to likelihoods, then talk about MMD estimators, and then I'll talk about how you can implement these efficiently in practice. Okay, so let me now start with the MMD estimators. Are there any questions at this point? No? Okay. So for those of you who might... Oh, yes?
No questions.
Okay. Okay, so I'll just move on then. Okay. So let me make this a little bit more formal. So I've already given this definition in passing, but what I'll call a generative model is a family of probability distribution which are indexed by a parameter. So my parameter will be theta. And so all my distributions will be defined on RD or some subset of that. And theta will be in RP. So this is mostly for me to define my notation. And so for every element of this family, so for every p theta, I can just generate realizations from the distribution. Now, usually the way I'm going to be representing these generative models is as a pair. So I'll be writing them in terms of two things, a base measure, U, or base probability distribution, and a function, g theta, which map from U space, which is where this U measure is defined, to the X space, which is where my distributions are defined. So to sample, all I need to do is sample from U, and then just apply this map to get samples from p theta. And what you see is that this map is indexed by theta. So all I need to do if I want to sample from a different element, let's say theta prime, is just change the parameter that I put into this map. So let me give you a very trivial example of a generative model. So a Gaussian location model. So my base measure or base distribution U will be just a Gaussian with mean 0. And then I can just take the map g theta to shift all of the samples by a constant value theta. And this will allow me to get any distribution which is of the form of a Gaussian distribution with some mean theta. So obviously, if I change the value of theta, let's say I use theta prime, I get one Gaussian, and if I get theta prime prime, then I'll get another Gaussian. So that's just really kind of like technical, perhaps definitions, but it's just to give you the setting in which I'm going to be working. And so the problem will be, I'm going to have some data. So this is the inference problem. I'm going to have some data yj from 1 to n, which are just realizations from some unknown true state of nature. And my aim, so to solve the inference problem, what I want to do is recover a value theta star such that Q, which is the true state of nature, and P theta star are as close as possible. So in the setting where Q is an element of my family, so for example, if my true data generating process is a certain Gaussian, then my aim will be to find the mean of that Gaussian given this data. And obviously here the setting is a little bit more general. So I'm also allowing for the fact that Q may not be inside this family. So it might be that, let's say my generative model is a family of Gaussians, but maybe Q is actually a mixture of Gaussians. In that case, there is no theta which recovers Q, but you just want to find one such that Q and P theta star are very close. Okay, so that would be the kind of general setting for the talk.
Would you consider that model misspecification if your Q is a mixture, but you assume it's only a single Gaussian?
Yes, exactly. Yeah, exactly.
Okay.
So, I mean, statisticians, the way they talk about this is they call this either M closed or M open setting. So M closed would mean that you assume that your Q is an instance of the family, and M open would be what you just called misspecified. Yeah.
Thank you.
And so what I'll be doing is I'll be talking a bit about the fact that you do need to consider both settings to decide what's a good inference method. So I'll talk a bit about robustness, and this will be mostly this M open setting where, or the misspecified setting where I want my estimator to still give a reasonable answer even if I'm not in the right family. And I'll get to this in a second. Okay, any other question? No? Okay, so I'll keep going then. Okay, so I have a very, very brief summary of the literature. And this is definitely a very bad summary of the literature because this literature is so vast that I have literally no chance of summarizing into one slide. But I'm going to give a very biased summary of the literature just to give you some ideas of what's in there. But that's definitely not everything there is. And if you want to see a better summary, you should go and look into the paper. But anyway, I'll keep on going. So one option that you have if you have a generative model would be to just approximate the likelihood of your model if you don't have access to it. So for example, it might be that in this example of the galaxy that I gave earlier, even though you can't write down the exact likelihood, you might be able to write down the likelihood, which is roughly okay. I mean, it's not correct, but it's close enough that you think it might not matter too much for your inference. And then you use your approximate likelihood to do inference, for example, in the classical way that people do. So either Bayesian inference or something like maximum likelihood estimation. So there's a whole range of methods that do that, and I'm not going to talk about them more here. Because I'm really going to assume that you cannot do that. But just so you know, there are these methods that do take this approach. Now, one approach which, one setting which is considered a lot in practice is cases where the likelihood is in fact known, but only up to some unknown normalization constants. So you could evaluate your likelihood, but there's just a constant that you don't know that would actually impact, well, that means that you can't really use things like maximum likelihood estimation or Bayesian inference. But then people use different kinds of approaches which minimize distances as well, but based on the likelihood up to the constant. So they just choose the distance in a convenient way such that you don't need to evaluate this constant. So the most well-known one of those is score matching. And I also have a small plugin for one of the method that I've worked on based on Stein's method, which is basically a generalization of this idea of score matching, which connects very much with what's in this talk today. So if you're interested in what was in the talk today, you can go and have a look at that paper too. So that's why I said it was a very biased summary. This is definitely not, what people consider to be the most standard method. It's quite a new one that appeared at NeurIPS last year, but I thought I would just mention it anyway. Okay, so otherwise, in Bayesian settings, when you have these unnormalized likelihood, this is usually called doubly intractable problems. So there's a lot of papers that have this title of Bayesian inference for doubly intractable problem. This means a normalized likelihood and unnormalized posterior. And I guess the setting which is closest to the one that I'm going to be considering is ABC, so approximate Bayesian computation, where there you usually assume exactly the same thing that I assumed, which is that the only thing you know about your model is just how to simulate from it. And you don't know anything about likelihoods or even just likelihood up to constants. So for those of you who know about ABC, what you should think about in this talk is that I'm doing a non-Bayesian version of ABC. Okay. So I realized this was a fairly rushed summary of the literature, but I thought it was important to do this just so that you have some kind of idea as to what people are thinking about. Okay, so let's talk about minimum distance estimation. So my methods, the method that I'm going to be talking about in this talk is one instance of this minimum distance estimation framework. And the way that it works is just you have an empirical measure, QM, which is just a measure which is made out of your data points. So here you should just think of this as the data. And what you will do is just look at the distance between your data and elements of your model. And you will just pick the value of theta, which makes the p theta as close as possible to your data. And so this value of theta will be the one that you choose to keep for your inference problem. Okay, so then obviously this raises the question of distance. I've already mentioned this. So one big challenge is actually finding a distance d which can be computed or at least approximated in a straightforward way for generative models. And in most cases of distance probability distributions, this will not be possible. So here there's a specific thing, which is that p theta, well, you don't really know anything about p theta from samples, apart from the fact that you can get samples from it. And QM is an empirical measure, and this makes it quite challenging to compute in closed form. So the main two examples that I'll be talking about in this talk is the Wasserstein distance and maximum mean discrepancy. So I'm hearing some more typing, so if you could mute your microphones, that'd be great. Thanks. So in both of these cases, you can actually not compute the distance in closed form, but at least approximate it in a straightforward way. And so these are, well, this is the main reason, in my opinion, that these two distances are very commonly considered in the literature. Okay. And both of them relate closely to this very classical method of statistics called the method of simulated moments. And so what I'll do is I'll take some time now to just recall what this method of simulated moment is. And then I'll show you how the Wasserstein distance and NMD are just can be thought of as generalization of this approach. Okay. So for the method of simulated moment, the idea is that instead of computing some very complicated notion of distance between distribution, what you'll do is you'll just summarize your distributions in terms of their moments. So what I need to do to use the method of simulated moment is define a bunch of functions. Here they're called MK, which are just summaries of your data sets, so moments of the distributions. So examples could be the mean of the distribution, it could be the variance. Maybe you could have different moments being different means in different dimensions. You could use more complicated summaries, but yeah, you have to define a set of moments. Then the way it works is that the first step is you just take your data set. So YJ here is my true data set. It's the one I have available to do inference. And I just compute all of the moments of this data set. So I just compute these moments, these summaries. And then what I do is I look at my model and I pick a bunch of parameter values as candidates. So here they're the theta t's. And what I'll do is I'll just simulate some data for all of the theta t's, and then I'll compute their moments. So now at this point, what I have is I have moments of my true data, and I have moments of my simulated data. And then what I can do is just pick the parameter theta t star for which the moments match best. So now I've just realized I have loads of typos on this slide. So let me explain what the typos are. So in step 2, the simulate x1 should say xt. So there's going to be a different, the index is wrong. But also the distance in moments should have a squared. So here I'm talking about distance squared. Anyway, so the summary of this is that you should summarize your true data in terms of moments, then generate some fake data, summarize it with moments, and then pick the parameter which gave the best matching moments. So here I'm talking about some weighted sum of moments. You could have some more complicated distance on moments. It doesn't really matter, but that's the main idea. And so this is something that's used a lot, for example, in econometrics. And the main challenge there is really that every time you have a new model or a slightly more complicated problem, you have to come up with new moment functions. And so you see all of these papers where they consider a specific problem and then they try to derive some good moment functions for that particular problem. And that's obviously slightly not very satisfying, because I don't really want to have to write a new paper every time I have a slightly more complicated model. And so there's really the question of how can you choose these moments in a more automated way. And so what I'm about to show you is that the Wasserstein distance and the MMD distance are both generalizations of this approach for specific choices of moments. Okay. So both of these distances, they can be written as integral probability metrics, which are distances on distributions which take the following form. And let me just discuss a little bit what this form is. So basically what you do here is you let's say for a fixed function f, what you'll do is compare the integral of f against p to the integral of f against q. So if the integral of f is the same, then you have some reason to think that the two are the same, and that p and q are the same. And obviously, if you do that for a very large family of functions, then it should give you more reason to think that p and q are actually the same if they match for a lot of functions. So here you can think of this exactly in the sense of moments, where instead of having just a couple of moments, I have a family of moments which are indexed by my class of function h. And the Wasserstein distance is just one instance of this class for specific choices of h. And similarly, the MMD distance is also just one specific choice of h in here. So the natural thing would be, of course, to look at this method of simulated moments, and instead of comparing these moments that have been handpicked, I'm just going to compare a very large family of moments indexed by this function class h. So that's the idea of the generalization. So the question, as I mentioned, is how do you actually compute this kind of distance? So here, I mean, you actually have to take this supremum, which could be quite nasty if h is quite complicated. And that's usually what's stopping you from using most distances that fall within this class of integral probability metrics. And so the main reason that people use the Wasserstein distance or MMD is that these are choices of h which make it more straightforward to actually compute this supremum in closed form.
I'm sorry, may I ask you a question?
Sure, yeah.
So the Wasserstein distance you're talking here is the dual form of the second Wasserstein distance, or general Wasserstein distance?
So this one, the one I'm talking about is the Wasserstein distance used in optimal transpose.
Yes, so I think is that only the like dual form of two Wasserstein distance can be written in this form.
Yes, you can't do it in the most general way. Only specific cases. That's true.
Yeah. Okay.
Yeah.
Thanks.
That's right. Yeah. So in the case of the Wasserstein distance, and here I'm being slightly imprecise in what I mean by Wasserstein distance, but for one specific case of Wasserstein distance, this corresponds to taking h as all Lipschitz continuous functions, and this becomes an optimal transport problem. But with the Wasserstein distance setting is slightly more general. And I'm not sure, I actually don't know if you can all write them in this integral probability metric form or not. Yeah. Okay. So let me just summarize. So what I talked about is this method called the method of simulated moments. And I told you that the problem is that you have to pick your moments yourself, and that's potentially difficult to do for some arbitrary model. And so what I'm arguing is that you should take, instead of comparing a fixed set of moments, you should compare over a whole family of moments, perhaps infinitely many, in the setting of, well, for example, as is done here. And this could be, for example, the Lipschitz functions, but it could be anything else. And what I want to do is both choose a very large class of functions so that I'm comparing a lot of moments, but a small enough class of functions such that I can compute this distance. So it's kind of this trade-off. Okay. Are there any other questions? So I've briefly mentioned the Wasserstein distance. Now, of course, the title of the talk is is not talking about Wasserstein distance, but about maximum mean discrepancy. And well, actually, maximum mean discrepancy is also an example of integral probability metric with a slightly different choice of function class. So I'm hearing some more typing, so if you could mute yourself, that'd be great. Thanks. So in this case, for MMD, I would have to take H to be the unit ball of some reproducing kernel Hilbert space. And because I don't know exactly how many of you will know about reproducing kernels, it doesn't really matter if you don't know much about reproducing kernels. What I want you to think about in this talk is just that my functions are going to be looking a little bit of this form, which is just a weighted sum of these kernel functions. So the kernel here, you can think of it as something that looks like a Gaussian distribution. It could be more complicated than that, but maybe that's the picture that you should have in your head. And so all I'm going to do is take my function space H to have functions of this form. Now, obviously, all of the properties of the function will be inherited from the kernel. So for example, if my kernel looks a bit like a sinusoid, then I'll have periodic functions. If my kernel is very smooth, then I'll have very smooth functions. If it's very rough, I'll have very rough functions, etc. So there's a one-to-one relationship between this function space and this kernel. And so I'll be mostly focusing on talking about properties of the kernel. Now, the nice thing that I'm also not going to show you how to derive, but that I'll just need you to believe me, is that the maximum mean discrepancy is just, well, it's an integral property metric where you take H to be some RKHS, or the unit ball of some RKHS. And why is that useful? Well, because in that case, I can actually rewrite it as an expression which doesn't have a supremum anymore. And that's really useful because now I've removed this issue of having to do this big supremum, which might be intractable. So here you can again think of this as a little bit in the framework of the method of simulated moments, where now the moments is just an integral of the kernel. And so usually people that work in NMD, they like to talk about this integral of the kernel against a distribution as the embedding of the distribution in the function space, because now this is an element of the function space. So what you're doing is, instead of trying to compute distances between distributions, which might be difficult, is you map every distribution to an element of a function space, and then you compute distances in the function space. And that's a lot easier to do. Because we can use all the tools from functional analysis. And one thing is that you can think of this as well as comparing infinitely many moments of the distributions, because this RKHS is, well, the function space is not finite dimensional, so there's infinitely many functions in it. It just so happens that you can compute the supremum in the closed form nonetheless. Okay. So I've already mentioned the kernel. One example would be the Gaussian kernel. And so that's the example that you should keep for most of the rest of the talk. So, okay, this MMD, I had the expression in the previous slides. I mean, this norm, you can actually evaluate it in closed form, and it's just now a bunch of integrals of the kernel. And so this is something really easy to estimate just by sampling from P and Q, and you can estimate these integrals. Okay. So now what I'm going to propose to do is to consider minimum MMD estimators, where my choice of distance is the MMD. And I'm just going to pick the parameter theta, which minimizes the MMD. So that's basically the same thing as doing the method of simulated moments. So when instead of choosing my moments one by one, I'm basically considering a class of function which has infinitely many functions, and I'm doing that in a careful way such that I can actually compute or at least approximate the solution. So in practice, I mean, this is very easy to do. evaluating this MMD squared, I can just approximate it using samples. So I just sample from my model, and then I end up with basically a sum of kernel terms. Okay, so the summary is I want to do inference. So given a data set, I want to recover a value of the parameter. And what I've done is just pick a convenient choice of distance such that I can do this in a fairly straightforward way. And this distance is this maximum mean discrepancy. Are there any questions about any of this? If not, I'll keep on going. So here, maybe I can make a small comment about what people do in the GANs literature. So in the GANs literature, they do exactly this kind of estimators, but where there's an extra layer of complexity, which is that they also take an extra supremum over the choice of kernel. So usually the kernel has some parameters. I've had the example here of the Gaussian kernel, which has a length scale L. And this is something that you need to pick. And so what GANs do is they try to solve the optimization problem exactly the same as here, but with an extra supremum over the length scale. And so they usually, then the implementation is some kind of well, usually you take gradient steps in theta space and then gradient steps in parameter space of the kernel, et cetera, until you find the good generative models. So here what I'm doing is slightly simpler. I'm not taking the supremum over this kernel or over what would be called the discriminator in this literature. But
I'm tired, I had a bad night.
So I'm still hearing someone talking. So I'm going to start muting people. This is fun. If I could find how to mute you. Okay, but anyway. So yeah, so that's the main difference with what is done in the MMD GANs literature. So in the GANs literature, there's also other distances considered. So you don't have to do MMD, you could use something else. But today I'm mostly going to talk about MMD, and I'm going to give some reasons for that in a little bit.
Sorry, may I ask a question?
Sure, yeah.
Again. So you're talking about GAN is some specific like MMD with some fixed kernel, but I guess it can't explain why GAN will fail to learn when we fix the discriminator, right? Because you see in the experiment when people fix the discriminator, which may corresponding to maybe MMD, like you said, with the fixed kernel, but why people just like can't learn the generator in that case?
Yeah, so the case of GANs, so the similarity with this, so in GANs, usually the generator is some kind of, let's say, complicated neural network.
Yes.
And so the discriminator, we can think of it here as the kernel, and maybe you change the length scale or something like that. So what you're saying is that in practice, what people in the GANs literature have noticed is that if you don't adapt the discriminator, then you can't learn very well. Is that what you're saying?
Or you train the discriminator to optimal, and you can't learn the generator either.
Okay, so I don't know exactly. I think the applications are slightly different. So in the stuff that I'm going to be talking about, the models are not some complicated neural nets that give you images. They're really more like physical models where each of the parameters has really like some kind of physical meaning. So there might be that in the case where you are somehow over parameterized, I think one of the reasons is probably that if you are completely over parameterized, you might end up in local minimum, and by changing the discriminator, that would allow you to kind of avoid these local minimum. Whereas if you don't change it, then it's you're kind of stuck. This is my intuition, but I don't know exactly much more than that, basically.
Okay, thanks.
But in general, the implementation of these algorithms is still difficult because you need to minimize over theta, and then maybe also maximize over the discriminator, and that's really just a quite messy optimization problem. So in general, I think the kind of gap in our understanding is probably in this, like, how does these gradient descents actually behave in these complicated spaces?
Sorry, just to follow up on that question.
Sure. I can only barely hear you, so if you can speak a bit louder.
Sorry, I've got a really bad microphone, so I'll try. Specifically the case where you have the perfect discriminators where there exists some function that can perfectly classify Q and P, and the discriminator finds it.
So what's the question?
Just in the GAN literature, the perfect discriminator is when the discriminator finds a function that perfectly differentiates Q and P.
Yeah.
And I'm trying to see that apply that to this slide.
Okay. Yes. So that's now, I apologize, it might be a tiny bit more technical, but in this literature on MMD, so I had a little comment here at the bottom. K is a characteristic kernel. So what this means is that for the MMD to be a metric on distribution, I be able to differentiate exactly. You have certain conditions on K. So there's loads of papers, some of which came out of Gatsby, that characterize, well, when is K a characteristic kernel? So if K is a characteristic kernel, then you know that it's a sufficient discriminator for your model. So,
okay, that makes sense. Thank you.
So if you want to, it's a technical condition that I'm going to assume from now on, but it's not a strong condition at all. So for example, in a lot of cases, most cases that you would care about, the Gaussian kernel would suffice for this. Yeah. So for those of you who are basically wanting to fall asleep soon, I have a takeaway message before the end. And the takeaway message is that the kernel will completely determine everything about your estimator. So every useful property that you could have from an estimator will just come down to which choice of kernel you've made. So let's think a bit about what would be useful properties for an estimator. Well, one useful property would be that my estimator is able to recover the truth. So that's the question we just had. But that obviously depends on the kernel. Then there's the question of how quickly in the number of data points, of true data points, can I recover the truth. That's usually called in statistics efficiency. And that will boil down to how you pick your kernel. Another property which could be useful, which we mentioned at the very start, is this question of the M open setting and close setting. So how well will my method work when the model is misspecified? That's completely determined by the kernel. And finally, how easy is it to solve this optimization problem? Again, completely determined by the kernel. And so basically, the rest of my talk will be just about how you should pick this kernel to get some useful properties. And so what I'll do is I'll present some theoretical results on these estimators and then try to analyze how they depend on this choice of kernel. Now, if you're worried about me presenting very technical results, don't worry. I've kind of basically hidden all of the conditions, and I'm just going to intuitively explain what these results say. And for those of you who want to know a bit more about the technicalities, you can go and read the paper. Okay. So to kind of motivate what to look at, I'm going to mention briefly what is done in the machine learning literature for MMD GANs. So there's a couple of things. So the first one is just to use a Gaussian kernel. So that's the kernel that I mentioned previously, or maybe, and just use that with a fixed length scale. And that might or might not work depending on your problem. Usually what people have noticed work slightly better is to have a mixture of Gaussian kernels. So that's just a weighted sum of these Gaussian kernels where I have different length scales. Now my weights, I can choose them, I don't know, maybe in a hacky way such that the method works well, or just all equal, or it's not, well, it is important in practice, but I'm not really going to comment on that. And the other point is that often if only one length scale is used, the length scale used is based on the median heuristic, which is basically a way to choose your length scale such that it is appropriate for your data set. So you want the length scale to scale with how spread out your data points are, and the median heuristic is basically a semi-automatic way of scaling this length scale. Okay. So let me start now first with, actually, I don't have that much time, so I might skip this section, but I'm just going to summarize what's in it. So the main point was going to be that to implement these estimators, you need to solve an optimization problem. And the way that people do that is with stochastic gradient descent. So they start first at some fixed value of theta, and then they do descent steps, perhaps approximating the gradient, so taking an unbiased estimate of the gradient. So I was going to talk about that, but I'm gonna skip it. The main point is that in this paper we have an efficient way of doing that, which uses the geometry that is induced by the MMD. So we have some kind of like analog of natural gradient descent that works specifically well for MMD. And I'm going to skip it, but it's really easy to implement, and it works much better in some cases. Maybe all I'll do is I'll just comment on this picture. So one of the points that I made is that the kernel really matters in terms of implementing the method. So this is some simple model where I'm plotting the loss function, or if you want the MMD, as a function of theta in the fourth dimension. So it's a 4-dimensional model. And I'm going to use a couple of different kernels to do so, to get a different loss function, or MMD, and see what happens to this loss function. So what you see is that if you choose your length scale to be very small, then you'll get something super flat, and perhaps it'll take you a very long time to get to the minimum, which is this dotted black line. So the blue line is too flat, and so your gradient method will really find it difficult. On the other hand, if you take larger length scales, it starts getting a little bit better. And for example, this mixture of length scales seems to work quite well. So this is just one simple plot that just shows you that picking a kernel for a specific model is really important, even just to be able to solve the optimization problem in practice. Okay. So that's just one summary. And I'm sorry that I'm having to skip, it's just that otherwise I would completely miss on the rest of the talk. So another point that's important is that you want your estimators to be robust. So if my true data generating process is not in the family, I still want my model to be able to recover a reasonable value of the parameter so that it's close enough to the true data generating process. And this really comes from, you know, the motivation really comes from this really famous sentence, at least in statistics, that all models are wrong, but some are useful. And so it's not because your model is misspecified that it should be completely useless, but it is important to kind of make sure that you're not going to infer really bad values of the parameters. So here, what I've done is I'm going to do a simple example to show you what happens if I have some of my data which is misspecified. So this example is my data generating process is going to be an SDE, which is from this Lotka-Volterra model. And I'm going to have unknown initial condition. So I'm just going to have some unknown initial condition, and then my SDE is going to simulate some process, and my data will be the final value after some time, big T. So you can see even here on the left-hand side plot that if I change slightly theta, i.e. the initial conditions, I get really different trajectories. And so I should be able to recover the initial condition from the final value after some time. Now, in this case, what I'll do is so I could just use my Lotka-Volterra model and use my MMD estimator on this, and that would work quite well. But here, what I'm going to do is I'm going to corrupt some of the data points. So I'm going to assume that the vast majority of them are coming from a fixed value of theta, and then maybe a small percentage of them will start at another point. So that's why I've plotted on the right-hand side. So the blue is most of the data, and the light blue is the corrupted. And so I'm going to see how my estimator is impacted by the proportion of data points that are corrupted. So this is what I have on this plot. So this plot, there's a lot in it, and so bear with me for a second. So what I've done here is I've plotted what happens with my estimator as I do gradient descent steps. And I've compared two different methods. On the left-hand side, there's a synchrone estimator, which is one of the common approximations of the Wasserstein distance. And on the right-hand side, there's the MMD estimator. So what I've done is some of the values, some of the data, I've put the initial condition being theta star, and the other one being theta dagger. And then the lines, the color of the lines correspond to how much, what proportion of the data was assigned to theta star and the other to theta dagger. So the main difference that, so as you see, if I pick any line, let's say, I don't know, the red line, it starts at 0 around 90, and then it goes up to 120, which is the true value here on the left-hand side. And the same happens on the right-hand side. So that's what we'd expect. And in this case, I've corrupted 0% of my data points. And so I'm able to recover the truth, happy days. That's it, basically. Now, obviously, the situation becomes different if, so obviously, if 100% of my data points are corrupted, that's the same thing as saying that theta dagger is the truth. And again, you see that it's able to recover that. Maybe the left-hand side plot, I should have plotted a bit longer so that we see it converge all the way, but it does converge. Now, what's happening in the middle is what's actually interesting. So if I look, for example, at, imagine, I don't know, 40% of my data points are corrupted. So that's the pink line. What you see on the left-hand side is that here, I'm not able to recover the truth anymore. But on the right-hand side, I am. So that's a little bit weird in a way. So what's happening is that, well, okay, one of the methods is able to recover the truth, the other not. But, and so what statisticians would say is that the method that's still able to recover the truth would be a robust method. It's not impacted by the fact that 40% of the data is corrupted, and the other method is not corrupted. So obviously, you could argue that you know, having 40% of your data corrupted, that's not really corruption. Maybe it's just that your model is you know, more complicated than you're assuming. But still, I think what's interesting is what's somehow in between extreme cases, so a lot of data corrupted or not. And the main picture is that here the MMD is able to be really robust. But actually, if I change the kernel, I would be able to get exactly the same kind of picture as the left-hand side. And that would be simply by changing the length scale. So here I've done this comparison with the synchrone estimator. And the synchrone estimator, this is just a standard implementation in the literature. It might be that you can do that as well, but it's not really well known whether you can or not. So that's at least one advantage of the MMD estimator. Now, there's a bunch of, I'm going way over time, so I'm going to have to briefly comment on this. So in the paper, we have a bunch of theoretical results that explain that you can make MMD robust under some condition. So there's different definitions of robustness. There's qualitative robustness, bias robustness, etc. And they each basically talk about robustness to different kinds of perturbations. And so we prove that MMD is robust to in these different definitions that are the most common in statistics. And so I'm going to skip that. The last point, so I think I'm just briefly going to mention that and then give an example just to summarize what I've talked about. So the last point is about consistency and efficiency. So maybe I'll skip right to the end to here. So what we've done in the paper is provide a central limit theorem for the MMD method. So this is just something saying how quickly my estimator converges to the truth as the number of data points increases. And here it's, well, it depends on square root of m being the number of data points. And the covariance function is some really complicated expression, which is here. And I'm not going to go into what this expression is, but the important thing is that it depends on this kernel. And so here again, you should be able to change your kernel to make your method either more efficient or less efficient, i.e. make this covariance bigger or smaller. And so what we do in the paper is talk about how you can do that in practice. So one thing is that under some mild conditions, if you take your length scale growing, you will recover the fastest possible rate, which is the same thing as maximum likelihood. Okay. So I'm just, it's a bit of a shame I took a bit too long at the start. Normally I do this talk in 1 hour. So I was a bit too slow. So I'm just going to summarize with one, well, I'll probably just leave it at this. So because we're about to run out of time, but the main summary is that I've considered estimators which are minimum distance estimators where the distance is the MMD, or well, some unbiased estimate of the MMD. And I've talked a little bit about, even though I kind of ran out of time, the fact that the choice of kernel allows you to trade off loads of different concepts. One of them being efficiency of the estimator, one of them being robustness of the estimator, and the third one being how easy is it to implement this estimator in practice. And so in the paper, we have a lot more experiments on much more complicated models.